we have two equations that we saw last year. We have the period of a mass spring system, and this is either a vertical or horizontal mass spring system, where m is equal to mass, k is our spring constant, and capital T is period, omega is still angular frequency, and F is regular frequency. Down here we have the period of a simple pendulum, which is simply a mass on a string, and T is equal to period, L is the length of the string, and G is positive gravity. Now let's do something very similar for the equation of motion for a pendulum. For a pendulum, we have an object on a string. Initially, it is pulled away from equilibrium and has an angle theta that it makes with the vertical. Again, the free body diagram for this object, we have mg going down, we have T going along the string, and then we normally get the components. Now here, it's going to be mg cosine and mg sine. Now, as this object oscillates back and forth, this theta is actually changing. So this force, mg sine theta, actually changes. So let's look at only mg sine theta. So we're saying that our coordinate system is like this. Okay, this is x and this is y, and we've done this before. Now, because mg sine theta is always changing, it's always opposite the direction of my displacement, similar to my restoring force of a spring. So this is negative mg sine theta. Okay, again, you can also say it's negative because it's going to the left. So we'll have negative mg sine theta is equal to mass times acceleration. Again, we can rewrite acceleration as mg as a second derivative of position. But now you can see that here we have a theta and here we have an x. So we need something that'll relate the two. Before I do that, I'm going to cancel out these m's. And what I'm going to apply here is a small angle approximation. And I'll talk a little bit more about this in class. Now, what the small angle approximation says, that if my angle is small, something less than 10 degrees, then the sine of theta is approximately equal to theta. And the cosine of theta is approximately equal, and again, we'll show proof of that in class. So here, in problems, it will always tell you, use the small angle approximation. It will say that, and we'll see problems like that in class. So that means I can replace this sine theta with just theta. Now the problem is I still need to relate x and theta, but we know that x is equal to r theta, because really this object is moving in at least a piece of a circle. Okay? So we can replace theta with x over r. So this is x over r gives me theta. So I'm going to replace theta with x over r. Now my r in this situation is going to be the length of the string. The reason for that is because the point at which the string is attached is technically considered my axis of rotation. So this is the equation of motion for a pendulum. Now we can go one step further and find the solution to this. And by doing that, we can apply the same reasoning that we did before, that x will be a cosine omega t plus phi, if we need one, and negative omega squared a cosine omega t plus phi. Again, the a cosine omega t's will cross out. And what we are left with, though, is negative g over L is equal to negative omega squared. Again, here the negatives will cancel out, and we're left with the square root of g over L. Now we can also derive that other equation that we gave you for the period of a pendulum if we say that this is equal to 2 pi over t, and we get t by itself. So that gives us t is equal to 2 pi L over g. Again, showing where these equations are coming from and not just necessarily giving them to you. Again, in class, I'll show you examples of what this problem might look like and what it might say in order for you to know this is the solution or this is the process you're going to be showing.